Okay, hello everyone. Welcome back to the Intercontinental Seminar Series of Gravity and Cosmology. First of all, I would like to thank everyone's here, and also in particular for those who have also joined our spring session in the 2 months ago. We had a very successful spring series, and it's time to resume our fall series session. So the first speaker of our fourth session today is Dr. Suddhasattwa Brahma. And Dr. Brahma, he got his PhD in 2015 from the Penn State University. And after that, he went to Fudan University, APCDP in Korea, and also McGill University in Canada. And right now, he is a Higgs Fellow in the Higgs Center for Theoretical Physics in the University of Edinburgh in the UK. So today he is now going to talk about entanglement and dissipation of the quantum origins of structure. So if you want to ask questions, please feel free to raise your hands during the talk. And so without further ado, please, the stage is yours, Sudo.
Thank you, Chayu, for the kind introduction, and thanks to you and the organizers for inviting me to give this talk. So yeah, I'm going to talk about things which might be slightly unfamiliar territory for cosmologists. So please feel free to stop me and ask me questions. I'm happy to not go over everything, but I'd rather that you understand the basics of what I'm doing. Good. So this is work in collaboration with Arjun Barrera at Edinburgh, Robert from McGill, David Siri, and the people in red are current or past students. Okay, so what do I mean by the quantum origins of the universe? Of course, let's be ambitious. We're cosmologists, so we want to know where did we come from. That's the most ambitious answer that a fundamental cosmologist can ask. But more realistically, whenever we think of quantum origin of space-time or quantum origin of the universe, we think that on Planck scales, usual classical space-times don't quite work anymore, and we need some description of quantum gravity, which might be some very non-commutative, non-fluctuating degrees of freedom in the UV. But that's not what I'm going to talk about today. Instead, what I'm going to talk about mostly today is about the quantum seeds of structure in the early universe. So I'm going to talk mostly about cosmic inflation. So this is much less exotic than many different approaches to quantum gravity. It's more or less accepted widely as the paradigm for the early universe. And I'm going to provoke questions about, if we take this hypothesis that everything that we see in large-scale structure of the universe originates from quantum fluctuations during inflation, how far can we push this hypothesis? What are kind of indirect observational effects that might lead to? So essentially, I want to ask, what happened here? So what are the cosmological puzzles we can think about when thinking about the quantum origins of structure coming from an inflationary era? So what is inflation to begin with is, of course, I think all of you are familiar with this. It's a phase of accelerated expansion, and it tells us that we can start with a very tiny patch of space, and inflation blows it up to make it the whole universe. And the canonical picture that people would use is that we have a slowly rolling scalar field of some field of some sort, which has a very flat potential. And during this part, it sources this phase of accelerated expansion. But that immediately tells us that the standard picture of inflation not only solves all the cosmological puzzles, this horizon problem, flatness problem, etc., but as we know, its crowning glory is that it explains all late-time inhomogeneities that, for instance, we observe as temperature and isotropies in the cosmic microwave background as originating from quantum vacuum fluctuations. So this is a very rare test bed for testing quantum mechanics. It's a rare interplay between where we are saying that the tiniest scales in the universe, quantum vacuum fluctuations, lead to the largest scales that we observe, so macroscopic scales of large-scale structure. So this is by itself, even if this is just considering quantum field theory in curved spacetime, it's a very unique test bed for quantum mechanics. And as observations have become more and more precise, the question we want to really push is, how far can we test this hypothesis? We know what the zeroth order tests are, and inflation passes all of those with flying colors. So can we push this a bit more and try to see whether this hypothesis breaks down at some point, or if it is verified to even greater precision? So in other words, what we want to ask is, can we go to microphysics beyond Einstein's equation? So of course, we know, as I showed you in that canonical picture, if I have like some scalar field of unknown origin, which rolls over very slowly over a very flat part of the potential, inflation can be explained in terms of Einstein's equations. But the questions that often get asked now is, why did inflation begin? So in other words, if we go back to this picture, why was the field to begin with in this part of the potential? Why wasn't it sitting at its minimum? And we know that there must be this phase to have reheating. So why did inflation begin? Why was the field here to begin with? Or questions such as, why is the potential so flat indeed? We know that even if we start out, if we stick in a potential that is very flat by choice, and there are quantum corrections, etc., that can upset it. So these are valid questions that need to be answered beyond Einstein's equations. So in other words, we need to derive inflation from something more fundamental. So one way to do that would be to start with something like string theory and see if we can derive inflationary potentials. And by that, I mean very flat potentials from something like string theory. The other way would be to say, let's do a bottom-up thing and try and see how far we can push this idea and how far we can consistently have the initial conditions, the kind of potentials we need to source inflation. And that's the second avenue, is what I'm going to talk about mostly today. And what is the standard law? So just to give you a flavor of the kind of consistency checks that I have in mind, let's look at what we usually say in inflation. We say that there's a scalar field. We can write down a homogeneous part of it, which sources the background. And that's what sources the energy density during inflation. And then there are fluctuations. So I usually put a hat on the fluctuations. I said these are the quantum vacuum fluctuations, and these the statistics of these are what we will observe later on at late time inhomogeneities. And the question is, how is this consistent? Because I'm going to treat the background as classical, because that is what sources energy in the Friedmann equations, and I'm going to treat its fluctuations as quantum fluctuations. And the only way I know how to make this work, and the most widely tested, this is the party line for inflation, if you will, is stochastic inflation. That says that the quantum fluctuation source the background. There's a coarse graining that has to be done over these long wavelength modes, which coarse graining has to be done for the short wavelength modes, which would then give me a stochastic equation for the long wavelength modes, with some noise term due to this, which some kicks due to this short wavelength modes. And in general, in this Tarbinsky's formulation of stochastic inflation, what one does is one writes down a stochastic Langevin or Fokker-Planck equation for these long wavelength modes and assumes a Gaussian white noise. So what I mean by testing these assumptions of inflation is essentially saying that testing these kind of approximations. Is this Gaussian white noise a good approximation? Should we have to go beyond this? Or is this enough? Is it okay to assume something like this and then follow the standard law for inflation? And let me give you the take-home message at the very beginning, in case you fall asleep after this slide, is that to have a consistent early universe paradigm, we require certain new perspectives of open EFTs. Of course, I'm going to explain what I mean by open EFT in curved space in order to explain non-unitary phenomena. So the kind of phenomena I have in mind are things like decoherence. We know that these quantum fluctuations, if they have to source late-time classical inhomogeneities, then there better be some sort of decoherence. There's dissipation, there's entanglement, and all these kind of things. To answer these kind of questions, we need an open quantum systems approach to inflation. And that's really the take-home message, is that these are methods that are very well understood in fields such as quantum optics, and has only been applied to cosmology for, let's say, the last 10 years or so, or at least more rigorously in the last 10 years or so. And this is what we have to do a systematic derivation for things like stochastic inflation, and to put inflation on a much stronger, rigorous footing. Okay, so what do I mean by cosmological open quantum systems? And to do that, we have to first talk about, why do I need to talk about these open EFTs? And in general, I'm thinking about open EFTs. By open EFTs, I mean EFTs that go beyond Wilsonian effective theories. So of course, first of all, effective theories are obviously relevant in physics all the time. We identify certain relevant degrees of freedom to describe physics as certain energy scales or length scales, and while decoupling details of higher energy scales. That's the standard thing that we always say. This cartoon is just telling us that, to tell us about the motion of a car on a road, I don't need to know the motion of the Earth around the sun. And of course, that's true. But then when we have dissipative effects, and that is effects that exchanges energies and informations between a subsystem and its environment, and when these dissipative effects are significant, then the low energy EFT is neither unitary nor local. And this is again like just a cartoon. This is just a cartoon to tell you like how things work. I don't know details of the systems, but for instance, if you consider waves in the sea, in the deep sea, the waves can be very well explained by a Wilsonian EFT. But the waves near the shore, because they splash onto the shore, that is not well explained by a Wilsonian EFT. One needs a non-equilibrium EFT to explain that. So this is just saying that in nature, we always find non-equilibrium EFTs whenever there is a significant energy and information exchange between a subsystem and its environment. And why is this important in cosmology? As I will motivate further later on, in gravitational systems, there's always some sort of UV-IR mixing. There's no well-segregated energy sectors. So usually what happens for Wilsonian EFTs is that we have some conservation law, which tells us that if I start with some low energy particles, I'll end with some low energy particles. In between, there can be all sorts of things happening. But if I start with low energy particles, I'll end with low energy particles. And this kind of conservation law is what allows us to write down the low energy Hilbert space in terms of operators only that affect low energy observables. But this, whenever you have UV-IR mixing, whenever we don't have a global energy conservation, as is the case in inflation or in cosmology more generally, there would be this need for having non-equilibrium EFTs. So again, this might be very familiar to most of you, but just to tell you what this means, sorry, this is a typo, this should be ds squared. So if we just write down the fluctuation in some gauge that we want, and we go to this Mukhanov-Sasaki kind of variable, we know the quadratic action for inflationary fluctuations or cosmological scalar fluctuations take a form that looks like this. And we can write down the Hamiltonian corresponding to this as comprising of two terms. A term that is the usual scalar field Hamiltonian in flat space, and then there's a squeezing term. So this squeezing term is just gravitational pumping of k and minus k modes. It's like particle creation. And this is what is special about cosmology. Now, what this means is that and this is again like for super Hubble modes, again, these are all things that are very familiar to most cosmologists. I apologize if I'm saying things which are very basic, but I just want to make sure that everyone is familiar with this. For super Hubble modes, this term dominates, which means that there's a lot of squeezing and the modes get inside a squeezed state. Whereas for sub-Hubble modes, it's as if they're in flat space. So as if it doesn't know about this curvature of space-time. And this means that they are in their quantum vacuum, or the so-called Bunch-Davies vacuum. And the reason to show this is to say that if I have during inflation, the Hubble horizon is more or less a constant, and modes exit the horizon, which means that this is the condition that the k becomes smaller than z prime over z. That means it's exiting the horizon, and then it re-enters subsequently during a Big Bang expansion phase, during radiation or matter domination era. And this means that a mode, if I correspond the physical wavelength of a mode to its energy, then this is not conserved, because a mode can have a particular energy at early times, and because of the expansion of the universe, the wavelength gets stretched. And so what would be part of my UV Hilbert space would come into my IR Hilbert space at some point, because the modes are getting stretched. And that's just an effect of the expansion of the universe. What inflation does even more is that it makes these modes go outside of causal contact. Of course, it exits the horizon and re-enters at some later point. Okay, so the goal of this is to say that, let's say I do not just have like the system degree of freedom. Let's say there is a way I can systematically identify a system mode and an environment sector. So the system mode, let's say, is my adiabatic degree of freedom. That's what we measure, like this. The statistics of that is what we measure, for instance, in the CMB. But let's say there's also some heavy field, there's some entropic sector that it couples to. And what this means, using a little bit of technical jargon, and if you're not familiar with this, don't worry about it, is that we have a total Lagrangian which has the free part of the system mode, a free part for the heavy degree of freedom, and then there is a part which couples these two. This is known as this influence functional in the language of Feynman Vernon path integrals. What this means is that now there's a branch. We always compute things in this so-called in-formalism in cosmology, and there's this plus branch and this minus branch. And what this kind of terms do, if there's a coupling, is that they refer to cross terms between the plus and the minus branches. And these are exactly the terms that are responsible for non-unitary phenomena, such as dissipation and decoherence. So our goal is, using some mathematical techniques, to trace out. So even if you're not familiar with this, no problem. The main idea here is that we want to trace out over this hidden sector or this heavy sector and use some hierarchy to organize the system dynamics such that we can write down an effective action for the system degree of freedom. However, that effective action need not be unitary anymore. That's the main difference with, let's say, standard particle physics effective actions that we're familiar with. And to do that, we have to sort of combine two kind of mathematical techniques. One of these open quantum systems that people are very familiar with in quantum optics and quantum information theory, for instance, and those of effective field theories, which high energy theorists use all the time. And the combination of these two is going to be what I call open EFTs. Again, this would become slightly more clear as I go along. All right, so the goal, the very big goal here is, of course, to derive an open inflationary EFT, which is capable of incorporating the so-called dissipative and diffusive effects. And we want to find their observational signatures. I'm not claiming that I have done this thing. This is like the broad goal that we have in mind. Of course, if I am able to find some smoking gun signature of these kind of effects, that would also be a smoking gun signature of the quantum origin of inflation fluctuations, which we don't have yet. So this is a very ambitious goal, but this is a saying that there are alternative probes that we can measure so as to capture the smoking gun signals of the quantum origin of inflation. Okay, so just to motivate this a little bit further, let's say that how long did inflation last? And we know that inflation creates exponentially large scales. That's part of the success story of inflation. We know that this is how it solves the horizon problem. I'm not going to go into details of this. I think all of you are familiar with this. So we know how long it has to last, for instance, to explain the horizon problem. But how long can it last? What is the upper limit on that? And one way to think about this is that the scales that we observe in the CMB only forms a very small part of this flat region. So one thing we can say is that it is the potential is very flat only for the region that we see. And then inflation stops immediately. But that would be violation of the so-called cosmological principle, right? This is also a kind of cosmological principle that only for the scales that we are here to observe, we had inflation. And then beyond those scales, inflation just stops. So let's say we need 60 foldings of inflation or something for some energy scales. And we say inflation lasted only 60 folds. But that's a very strange thing to happen. It's almost like it lasted only 60 folds so that we can observe it. But that's not quite, so that assumes that we are special. What is more natural to assume is that if this is us, if this is our Hubble patch, then inflation probably lasted much longer. And it created a huge range of super Hubble scales. And we don't know what is the upper limit on this, but it's natural to assume that it did not last only so much that it explains our horizon problem. And I'm just giving this example to motivate how we can have this environment degrees of freedom which are hidden. So let's look at this. If we have some sort of microphysics, then there would be some long short mode coupling. So indeed, most inflationary models are not single field. It can be effectively single field for the degrees that we observe, but if we want to have some UV completion, we need additional fields. And if you have this kind of microphysics of having additional fields, they lead to long short mode coupling, which means that if we are here or here or here, that matters. So our observations only probe the effective theory for one given Hubble patch. So where we are with respect to this very long wavelength mode does matter. And that will affect our statistics. So everything that we measure, although we can never measure these long wavelength modes directly, but it has been shown that it does matter where we are with respect to these long wavelength modes for the observations that we make in our Hubble patch. So that's just an example of these very long wavelength modes, which we will never be able to measure directly. And also remember, these are IR degrees of freedom. So these are not the usual UV degrees of freedom that we can, Wilsonian renormalization way integrate out. So these are very IR degrees of freedom, which can be there, which we are never going to be able to observe directly, and yet can affect our observations. So that's an example of this hidden sector. And more generally, space-time horizons typically imply open EFTs. So gravity creates the space-time boundaries called horizons, which limit what we can observe without restricting the flow of energy and information across it. So of course, the very famous example is of black holes, and the other example is of de Sitter space. Now, the example of de Sitter space is more interesting because the de Sitter horizon is something that is observer dependent. So there are different open EFTs for different observers. And open systems, of course, is not a new concept. The entanglement structure of the quantum vacuum in black hole or de Sitter space-time has been studied for a very long time. And there's some renewed interest from completely different perspectives than what I'm talking about today. And even open EFTs for inflation, as I said, over the last decade or so has been gaining a lot of interest, precisely for this reason that we have realized that there is a lot of environment degrees of freedom that we are never going to be able to quantify exactly or observe directly, and yet they can affect our observations. So let me take a break here to tell you a joke that I heard when I was a graduate student. And the joke goes like this. So a physicist is lost in a hot air balloon, and she looks down and finds a person standing in a field and asks him, "Hello, where am I?" So she's lost, she's just screaming out, "Where am I?" And the man thinks for a bit and then replies, "I think you are in a hot air balloon." As the balloon flies away, the physicist concludes that that person must be a mathematician. The answer was absolutely correct in a very precise sense and was utterly useless to me. So this was a joke that I heard from a very famous mathematician at Penn State, and the reason for repeating this is that so that you don't consider this theorist working in fundamental cosmology to be a mathematician. So why should you care about these open quantum systems in inflation? If you are an observational cosmologist, or if you are somebody who does phenomenology during inflation, what is it to you how can I sell this story to you? Why is it of any interest to you at all? Why should you listen to the rest of the talk, in other words? And the idea goes as this: we want to learn about the early universe from observations, of course. That's the main idea. And the whole hope was that, once we find non-Gaussianities, those would put constraints on the model space. And we can then say, like, okay, these models of inflation are ruled out. These are the models that are still applicable. But we haven't observed non-Gaussianities yet. So that direct approach cannot tell us anything more. The most vanilla slow roll single field inflation model works very well. So we need a fresh perspective to think about how can we put constraints on model spaces of inflation. And there are many non-trivial predictions of inflation that come from non-perturbative regimes. So all the computations that we do are, of course, typically in perturbative regimes. But there are many non-trivial predictions, such as for primordial black holes and their candidature as a dark matter candidate. So those kind of things, having massive galaxy clusters coming from inflation, those come from non-perturbative regimes of inflation. Just to give you an example from this fairly recent paper by Vassar, Venot, and others, what we observe, like, let's say we have some probability distribution function. So from the tails, the peak of this function is where you can apply perturbation theory, and that coincides very nicely with the Gaussian PDF, with very slight differences. But the tails is where all the story lies. The tails is which will tell us about this production of primordial black holes and so on, because we need a very large fluctuation to produce something like primordial black holes. So those comes from the tails of the distributions. And the tails is where this distribution is going to be different. If it is not truly a Gaussian and something else, this is exactly where it is going to be different. So we want to find ways to compute this kind of probability distribution functions in regimes where standard perturbation theory doesn't work anymore. And what we want to do is, given realistic models, these open EFTs would tell us, give us indirect predictions through these tails of these PDFs over and above the direct predictions for non-Gaussianities, as I mentioned. So open EFT is a way to capture these effects. So dissipative and thermal effects, for instance, can lead to very large primordial B fields. So if the dissipative effects are very large, that we can mimic this as a thermal state during inflation, that actually gives a prediction for large magnetic fields, primordial magnetic fields. This is some work under progress with Arjun Barrera and a student here at Edinburgh. And again, there are vector modes can affect structure, can affect cosmic tensions. This is work with Stefan Alexander, Arjun, and Mike Toomey and others. OpenEFTs can better capture clustering effects on gravitational wave propagation. And this can affect, for instance, measurements that have been made by nanograv. This is some work done with Sadegh, Koshver at Edinburgh and the student. So I'm not going into details of this. These are not things that I'll talk about today, but just to tell you that what we want to ask is, when does this dissipative effects affect observations? And that, as I mentioned, would be a signature of the quantum origin of inflation. And this is the most interesting thing to do, but of course, this is the most difficult thing to do. This is a very ambitious thing to state, that we would be able to find like an exact signature that will tell us, oh, this is a dissipative effect. This means that inflation has a quantum origin. But it also does something for conceptual issues, like the stochastic framework, as I mentioned, for eternal inflation, for UV completion. So if we need a second field, it tells us something about that. And indeed, also about this so-called swampland constraints, as I would very briefly focus on for a second later on. Okay, so I think this is a good time to stop, because this is like the general overview. I'll give you some more details about things next. But if you have any questions, please, this would be, I'll be happy to answer them now.
Are you saying that quantum comes from dissipation, or rather dissipation implies quantum? I didn't quite catch that part.
Oh, yeah, in here, I truly mean by quantum dissipation. So I have like some quantum system, and I will explain what I mean by dissipative effects in a second, but I do mean quantum dissipation, yes.
But what I mean is that, is there not other ways to, is it an unequivocal proof that these fluctuations are quantum?
No, that's what we want to see, whether there is I mean, if I can find a smoking gun signal that, oh, these are if this effect comes up, then this must be quantum. That would be that's like the big goal. But I don't have that proof.
I see. So we're not quite there yet, but
no, not at all, not at all. If that was there, that would have been my first few slides. No, we're not there yet. But that's the goal. That's why we want to study these kind of methods, to see whether we can get some signal like that.
Okay. Thank you.
All right, so let's first talk about secular divergences and non-perturbatory summations. That's one thing that the master equation formulation does well. So what are secular divergences first? So many gravitational puzzles appear at late times. For instance, eternal inflation, the black hole information loss paradigm. And what it means is that if I write down the free Hamiltonian plus some interaction, can I write it like this? Can I do this approximation? And the answer is, of course, if t goes to infinity, then standard perturbation theory will obviously fail, no matter how small this lambda is, because then, so at late times, this kind of an approximation would fail. Although this is a very generic issue, when I present to you like this, why did we not learn about this when we studied QFT from textbooks? And that's because QFT from textbooks typically have colliders in mind. So we want to compute things like scattering amplitudes. And when you want to do that, then we assume we have asymptotically free particles to begin with and asymptotically free particles at the end. And in between, they collide for a short, finite period of time. However, gravity is different. There is no way to turn off gravity. Even if you have free fields to begin with, once you turn it on, once you turn gravity on, they would always be interacting. So if that interaction persists, and that means that gravity is an ever-present medium, so we cannot do this kind of an approximation, because at late times, obviously, this is going to fail. And late time secular growth has been shown. I mean, people have been studying this for quite some time now, and this leads to breakdown of standard perturbation theory in cosmology as well. I was saying more generally about gravity, but of course, this applies very well to cosmology. People have been studying this, as I said, for some time now. So let me give you an example of this kind of secular divergences, I feel, which is this momentum space entanglement entropy. So let's consider this coupling term, which is the leading order coupling term in the coming just from pure GR. So pure GR is nonlinear. It gives you cubic couplings. That's how you compute, for instance, the bispectrum and so on. So we use the similar kind of interaction that one uses to compute the bispectrum for single field, slow roll inflation. And for this kind of a coupling between system and environment modes, so environment here for me are the sub-Hubble modes during inflation, and the system modes are the super-Hubble modes. Of course, modes continuously go from sub to super-Hubble, as I've already mentioned. So if I want to have this system, I use these bands of momenta to compute the entanglement entropy. What's the entanglement between the red and the blue band? That's essentially the question I'm asking. So I won't show you details of this, but people had formulated how to compute momentum space entanglement entropy for flat space earlier, and we heavily used their work to show that for inflation, you find a result for the entanglement entropy density that goes like this. So this part, the thing in blue, could have easily been even guessed by power counting. The thing in red is the interesting bit, though. This tells you that there is a secular divergence here. That this tells you that what is the entanglement entropy at some time in some time t, which is given by a of t. A is the scale factor, normalized with respect to the beginning when inflation began. And we are assuming here that all the super Hubble modes were created during inflation. And then this is a very big number, right? There's exponential expansion of the universe. So A goes as like exponential of cosmic time. So this is a huge number. And that tells you that this perturbative entanglement entropy, an entanglement entropy that is perturbative clearly because this is zeta cubed term. So that's very, very small number, and also suppressed by slow roll parameters. This would become large at some time in the future because this is a very big number. So this is exactly, and we then did this computation later on with students at Edinburgh for a spectator field in de Sitter space with a phi cubed interaction. So it doesn't even have to be inflation. If you just have a spectator field and you do a similar calculation, you get a very similar result with this kind of secular divergences. And one can ask, at which point does this perturbation theory break down? And what we found is that if we say that there's an upper bound on this entanglement entropy coming from the thermal entropy of reheating, then I equate this to a thermal entropy of reheating, and then we find that the perturbation theory breaks down around this time, which is known as a scrambling time of de Sitter. And that's an interesting coincidence because if you are familiar with the swampland conjectures and so-called Trans-Planckian censorship conjecture, that's exactly the same time scale. So that's just saying that the perturbation theory fails on the same time scale as which people have assumed this that this TCC conjecture tells you also this similar time scale. So this is a purely QFT calculation, doesn't know anything about field theory, doesn't know anything about string theory or quantum gravity or anything. And it says that perturbative calculations fail on the same time scales as what is expected, let's say, from some UV completion of inflation. Okay, but what does non-perturbative resummation mean? So let's again take a heuristic example of particle decay. So we know that for particle decay rate, we can assume this kind of an equation, and we trust this solution for this equation, even though the decay rate itself is computed in some order in perturbation theory. So let's say quadratic order or something. Now the question is the evolution. So the question is, the evolution equation does not depend explicitly on time t. And that is exactly why we are able to trust this equation, even though this decay rate is computed at some order in perturbation theory. And the intuitive reasoning of trusting this versus this for gamma t much bigger than 1 goes as follows. So this is, I must say, this is an example that I learned from Greg Kaplanek, so all credit to him. And the idea goes like this, that if you, between any time period, let's say from 0 to T2, the equation tells you that the number of atoms goes like this. And you can continue this for the same time period between T1 and T3, T3 and T2 and T4, etc. And then you do the envelope of these terms, and that's exactly the exponential decay rate. So that just says that it doesn't matter which interval I choose, the decay rate, the number of particles always decays in the same way, and that's why I'm able to trust the envelope of this. And that just says that this is a non-perturbative resummation. So that what I would naively had said that, oh, but standard perturbation theory tells me I can't go beyond this when gamma t is order 1. Now I can go beyond this when I do this non-perturbative resummation, which is an intrinsic thing in this case, in terms of the decay rate. Now we can do the same thing in cosmology. So let's assume like a tau. So for the interaction that I showed you earlier, I want to find out what is the reduced density matrix of the system degrees of freedom, which are the super Hubble modes. And I start with the approximation. This is a Born approximation that initially the density matrix is a factored density matrix between the system modes and the environment modes. And I also assume this Markovian approximation, which is this, in this particular case, is just going to be the time locality. So it's not quite Markovian, it's just time local approximation for people who know about these things. And then one can write down this so-called Lindblad-like equation that looks like this. This is the time locality approximation, that this is bigger than 0. So this is what I mean by Markovian. These are dissipative coefficients. We don't have to get into that details of this. We can use the solution of this master equation to compute the power spectrum. And this is what we have done in this paper with Arjun and Jaime. And one can show that, of course, at 0th order, you get back what you expect. That's the scale invariant power spectrum that we're all familiar with. And then at 1st order in perturbation theory, we can compute this using numerical techniques. And we find a result that looks like this, where n is the number of e-foldings since this particular mode crosses the horizon. And this obviously, again, and this alpha is something that, again, you can do, this part you can do by power counting. The number in blue is something you get from the numerical integrals. So there's no control over that. I don't have any control over that. And what this tells you is that at some point, this number is going to be order 1, and this approximation is going to break down. But what we can do is we can treat the master equation as a bona fide dynamical map. So although the master equation is derived at some order in perturbation theory, I say that, no, this is my exact dynamical map. And then you do one further kind of arbitrary approximation that you ignore the decaying mode and you solve this so-called transport equation for the power spectrum. And you find that the power spectrum has a form that looks like this. And what gives you some confidence that you can trust this is this you can exactly compute analytically. And now this alpha number is exactly computed analytically. So this blue number now is some analytic numerical factor. And this matches very well with the numerical integration that we had done earlier. So this is an analytic factor now, which matches very well. And that gives me some confidence that this non-perturbative summation works well. And of course, now this is valued well beyond this alpha and goes to order 1. So master equations allow us to have non-perturbative summations. And this matches exact results better than standard perturbation theory in toy models. And I'll tell you of a toy model next. Okay, so just to give you a pictorial description of that, if I just use the standard perturbation theory, that will become invalid at some point very soon. But the late time resummation makes the power spectrum take a form that looks like this. So this really is very different. So for short times, they match perfectly. At very large times, the late time resummation works very well. So the master equation can do that for us. So now I'm going to tell you very briefly about why we need actually non-Markovian environments in cosmology. So non-Markovian means an environment which has its memory. So let me tell you in a little bit detail what that means. Why do we need to have time non-local master equations? So if I write down the system density matrix, that I just take the trace over the environment of the full density matrix, and I want to write down a master equation or an evolution equation for the system density matrix alone. And of course, the right-hand side does not depend on rho system alone. It also depends on rho environment, because I'm going to take the trace over the environment to get this. And one can formally do this by assuming that there's an interaction Hamiltonian, which is operators of the system and operators of the environment. And tracing over the environment can be written down in this so-called Nakajima-Zwanzig form. So this is a master equation that is, again, well known to quantum optics people. So suppressing all sort of spatial indices, one can show that this master equation depends on this kernel. This kernel that I call this is called the memory kernel K. And the idea here is that the memory kernel captures environment correlations. So if this kernel is very sharply peaked, if I replace this by, for instance, by delta function, then the right-hand side would become a local thing. And that's exactly the idea, is the integrand, if that varies slowly compared to the rest, compared to the kernel, width of this kernel, then I can approximate the master equation as a time local master equation. Otherwise, I cannot do that. So the whole idea here is that the system becomes time local only under this approximation. And that's precisely this locality approximation of this so-called Markovian approximation. Now, why do we not have the Markovian approximation is because when the environment has very large degrees of freedom, we very quickly achieve thermal equilibrium. And this is known as the stationarity, or this no back reaction of the system on the bath. So then the environment is just the environment. That's just a thermal bath. And whatever the system dynamics does, it has no effect on the bath. And Markovianity also has a different way of thinking about it, which is it has no information backflow. So information can only flow from the system to the environment, so a subsystem to the environment. And there's no backflow of that. And that, again, is dependent on the fast decay of these temporal correlations, so this fast decay of the kernel. So only then the past history would not be important. So what does non-Markovian mean, on this non-time local mean, is that if I start at some time t0, I go to t1 and go to t2. Usually in physics, we say, okay, where the state was at t1 doesn't matter. As I start with t0 and I went to t2, all that matters is now that I'm at t2. But non-Markovian means that no, the path matters. How it went from t0 to t2 does matter. And that is seemingly important in cosmology because of things like such as homogeneity and isotropy. These are symmetries in cosmology, which means that we would to have like a very large environment at linear order, because only k modes can couple to minus k modes. That's just that conservation momentum, which comes from this homogeneity and isotropy approximations. So to have infinitely many environment, we would need to have infinitely many environment fields to have a very large environment. And again, this is just a heuristic argument to say that cosmological environments are typically out of equilibrium. So that's why we would require non-Markovian master equations. And this is just a heuristic argument. We should now go and check, how does the kernel of environment correlations look like? Are they Markovian or non-Markovian? And that's what we did in this work, to show that let's assume the Markovianity approximation first and write down what is known as the Lindblad master equation. We can compute the perturbative correction to the graviton propagator during inflation from graviton loops. So this is just the tensor power spectrum, the one loop correction to that due to tensor loops itself. As far as I know, this had not been done before this, but people had done similar calculations before. There would be this kind of secular terms that I mentioned before. I've suppressed that because we know how to resum them, so let's ignore them for now. But this matches exactly loop corrections to the graviton propagator under the Markovian approximation that people had done using this in formulation. So again, to the best of my knowledge, no one had done this exact calculation from graviton loops, but people had done this from conformally coupled scalars or other things like this. And the answer is of exactly the same form as that. Mu here is the renormalization scale. Now we can go back and check how good was our Markovian approximation. So we can really write down, we can compute the kernel and see whether this was like very sharply peaked or not. And what we find, sorry for this long expression, is that the kernel is indeed very sharply peaked, but it's not delta function peaked. So the Markovian approximation seems to be a good one, but how good it is, we can only find now if you use this kernel and find deviations from the Markovian approximation. Only then we can measure the effect of non-Markovianity in this kind of quantum corrections. And this was done in this earlier paper also with Arjun and Jaime. All right, so how am I doing with time, Cheyu?
You still have like 15 minutes.
Okay, very good. So one question that people have asked often is that, let's say there are these non-local time terms, non-local terms. Can they affect late time dynamics? And this has been a question that has been asked for various perspectives, but one perspective is that, well, stochastic inflation is believed to provide the leading order resummation of these IR divergences that one finds during inflation with local equations. So why should, even if they're non-local terms, maybe they just all die out at late times, and all we need are the local terms in the evolution equations. To say this a little bit more precisely, there's a very rich literature of computing graviton loop corrections to, let's say, the conformally coupled scalar or photons in de Sitter space. And those kind of loop corrections show that there are secular terms in the final answer, but all the secular terms come from time local terms in the evolution equation. So indeed, the evolution equation also has non-local terms, and this is like heroic calculations done by these people and many others. My apologies if I'm missing some people here. Those are covered by these dots. But these non-local terms were shown to decay at late time. So if I compute the correction to the mode function of a conformally coupled scalar or photon due to graviton loops, then we would find that the conformally coupled scalar would know about the background evolution now through these loops of gravitons, but in a way that the non-local terms decay at late times. So even if there are non-local terms, do they even survive? These calculations would seem to suggest no. But remember, they were very specific calculations done for like conformally coupled scalars or photons, or even minimally coupled scalars and fermions in some cases from graviton loops. So we decided to test this hypothesis. So, and using a toy model, just in case I don't have enough time to go into the details, we showed that secular divergences can actually just as easily stem from non-local or non-Markovian terms. And more importantly, such terms can still be resummed at late times following a very precise algorithm without the need of any arbitrary approximations. And the memory kernel in such a toy model corresponds, in the same model, can affect other physical observables differently. So for instance, the memory kernel can affect the power spectrum in a way that the power spectrum depends on non-local terms at very late times. So the corrections to the power spectrum comes from non-local times, even at late times. Whereas other observables, such as, let's say, the purity of the system, so the quantity that measures decoherence, comes from the local terms in the memory kernel. Those are dominated by local terms, and those do not depend on this non-local terms so much, or the local terms dominate. So different physical observables can depend on the local or non-local parts of the memory kernel. And that's an interesting finding that I did not expect to have. Because of all of this work, I was expecting that at late times, it's always the local terms that would dominate for any observable, and that's not true. And this is some very recent work that has been put in archive with Jaime and my PhD student here, Xiankong. All right, so what's the toy model? The toy model is that the environment field is a conformally coupled scalar and the system field is a massless minimally coupled scalar. This is a model due to Boyanovsky from 2015 and also studied by Hollywood and McDonald in 2017. Why is this a good model for stochastic inflation? Is because the conformally coupled scalar is like a free field. So the sub-Hubble modes are the modes which are almost like in flat space. They don't know about the curvature of space-time. So that's exactly why they're modeled. This is a good proxy for the sub-Hubble modes, the conformally coupled scalar. And the adiabatic degree of freedom is the massless minimally coupled scalar. So this is the interactions. I'll be a little bit more detailed here because I'm saying things much more heuristically earlier. And the details are like, this is the action. I can put Bunch-Davies initial conditions for my system field, which is this one. So the system field is the usual massless minimally coupled scalar, and this is the environment field, which is the conformally coupled scalar. And I can compute the memory kernel, and the memory kernel beautifully splits into two parts. This is the non-local part, and this is the local part. As you see, this is clearly delta function. So that's why we choose this toy model, because there's a nice simplification to be had. One simplification is that the memory kernel nicely splits into this time local and time non-local bits. So I can then later on check what are the corrections coming from the local bit, what are the corrections coming from non-local bit, which is not easy to do in a realistic system. And the second is that, of course, this system appears, if you go back here, the system field is at best quadratic in the Lagrangian. So it's a linear system. So I can just work with any given P and the sum over independent momentum. So there's no momentum coupling. That's the nice thing about this model. So this is easier to handle. Okay, so the TCL2, so this is known as time convolutionless master equation. Again, if you're not familiar with this, don't worry about it. I am just writing down an evolution equation from the reduced density matrix corresponding to the system degrees of freedom, where this effective Hamiltonian is just the quadratic Hamiltonian and some correction terms. So these corrections are like known as these lamp shift corrections, which are just like renormalizes the energy spectrum of the free field, for the system field, sorry. And this dissipator matrix contains these diffusion terms and dissipative terms. And the reason to show you this horrific long equation is to say that just remember one thing, the terms in blue are the terms coming from the local part. Everything in black are the non-local terms. And the red is like a UV divergence, which comes up. So I'll have to assume like a mass counter term to counteract this UV divergence. So that's the only thing. Now, this is important because as you see, only D11, one of the diffusion terms has a contribution from the local term. Everything else only has contributions from the non-local terms. Of course, D11 also has contributions from non-local terms. That's something that's going to be important. Because one thing I want you to keep in mind is that the dissipative terms, so the deltas, are what matters most for corrections to the power spectrum. And the diffusive terms, the Ds, are what matters most for decoherence or purity. And this is going to be important in the very next picture, which is we computed the power spectrum. This lambda is the strength of the interaction. So this is, of course, lambda over h order 1 is where perturbation theory breaks down. So we shouldn't take this seriously. But this plot is just to show that these look like they're divergent. But if I plotted them for longer time periods, then they would also have this kind of non-perturbative resummation inbuilt into them. So this is the power spectrum appropriately rescaled in dimensionless units, so that we would find that there is no secular divergence, and they all give you a late time resummation, non-perturbative resummation. Horizon crossing here is when A is equal to A star. So this is when the mode crosses the horizon, for clarification. And what we checked is that if I go back and now turn off this local term, so let's just by hand put these terms to 0. So this one was already 0. Just let's put this one term to 0, which was the one local term. Even then, that does not affect the power spectrum at all. That's completely independent of it, because it's very subdominant, and the dissipation kernel is what really affects this quantity. So this first tells me that the late time secular divergence that would have happened would come only from the non-local parts of the kernel. So that's a non-Markovian effect. And I can use standard perturbation theory to compute the power spectrum, and then I would have exactly a secular divergence. See, this goes as like some number times n squared. Again, this number just comes from h over mass Planck squared kind of things. But this is the point, that this is the number of e-folds since the mode crosses the horizon. If I wait long enough, this will become big enough so that this perturbation theory will fail. But the master equation formalism automatically resums this divergence. And we actually go back and check this model with what people had done in the literature earlier, using sort of arbitrary assumptions about ignoring this so-called decaying mode and so on, to check how well does their approximated analytical results for resummation matches with our exact numerical results for resummation. And this is the comparison between the two. As you see, for lambda over h order 1, this is when perturbation theory breaks down. So that's a bad approximation. That's when they don't match very well. But for all smaller lambdas, the delta p over p is the difference between our method and this analytic methods divided by the exact result. And this is very, very tiny. So what we are finding using this exact numerical results is that the resummation works very well compared to this ad hoc approximations that people had done earlier to find analytical resummations. Now let's come to decoherence. So one observable is, of course, the power spectrum, but there's another observable, for instance, which is the decoherence. So because this is a sort of a Gaussian system, a pseudo-Gaussian system, so we can capture all of its effects from the covariance matrix. So the sigma 1,1 is the configuration space power spectrum. That's what I showed you. And now what I'm showing you is something that depends on the determinant of the covariance matrix. That's purity. Purity is a good measure for decoherence. And we find that states indeed start at 1, and then once it crosses the horizon at here, it soon decoheres as we expect for inflation. So once a mode becomes super Hubble, they decohere and become classical. So this is rapid decoherence. But this seems a bit weird because there's no effect of this non-Markovianity, etc. This is exactly what I would expect from a Markovian system. So what happened for non-Markovianity? We just said that the non-Markovian effects last at late times. That was the whole argument here. And the point is because decoherence is controlled, as I said, by these diffusion terms. And one of the diffusion terms does have this non-local term, has this local term. And although this looks like this goes as 1 over tau cubed and this goes as 1 over tau squared, so as tau goes to 0 at late times, this seems like the non-local terms would dominate. But actually at late times, if we do this expansion, there's some magical cancellations happening such that the local term dominates. And that's why the physics of decoherence looks as if there's in a Markovian system, as if it's the local terms that matter. So once it crosses the horizon, it's really the local terms that matter. And this is a pictorial representation of that. The yellow curve is what would happen if I just put the non-local terms to 0 by hand. The green is if I just kept the non-local terms. The pink is if there was no interaction. So pink, no interaction, the system remains pure for all times. If I just had the non-local interactions, indeed, the purity would oscillate. And that would not decohere and would not give us a classical system so easily. But the blue curve is a full purity, including both local and non-local terms. And that's very well approximated by the local terms. So that's why the local terms dominate for the purity, but not for the power spectrum. So I think this is like my second last slide. And the idea here is that, okay, I've told you that we need open systems. I've told you also that we need non-Markovian open systems. And what are the kind of cosmological consequences? So first of all, let me just mention one thing, that purity is sometimes difficult to compute, and we need other measures. And one such measure is this quantum complexity that we used for cosmology in this paper recently. But in solvable Gaussian models, people have indeed found novel phenomena for non-Markovianity, which is known as recoherence. So this plot is the best way to show that purity goes down and then bounces back up again for certain parameter ranges. And this can only happen in a non-Markovian system. And this was shown by Thomas Collard, Julia Grant, and Vincent Venant quite recently. And we are trying to also find other non-realistic models, let's say. So this was a very simple, solvable Gaussian model. We're trying to find in realistic models if we can reproduce similar behavior. And non-Markovian systems actually also have this unique feature that they have transient negative entropy growth. So that like violates second law. But that's never a problem because the overall second law is always in a laboratory experiment, always satisfied even for non-Markovian systems, because the entropy you spend to set up the experiment is much bigger than the little bit of entropy decrease that you would have during the non-Markovian experiment, let's say in quantum optics. But in cosmology, this is a very weird thing because in cosmology, the system is being set by nature. So it seems that there's a weird way to arrange. If indeed we find non-Markovianity to be a significant thing, or parameters such that non-Markovianity is significant, that we have this kind of purity bounce, purity freezing, or recoherence, then that would lead to non-Markovian negative transient entropy growth. And this is just for those same parameters that for which I showed you this recoherence for the same kind of parameters with Jaime, Xiankong, and David Siri. We computed them for the rate of change of the entropy, the entanglement entropy, and you see that the entanglement entropy goes negative for a small while here. The rate of change goes negative, so that's a negative entropy growth. Again, what we are currently working on with the same characters is that are slow roll attractors special? And what if I have some non-attractor ultra slow roll phase? These are exactly what is interesting for things like primordial black hole production during inflation. So if there is some similar ultra slow roll phase in between some slow roll phases, does that lead to some visible consequences for things like purity and decoherence? And these are very preliminary results. The paper should be out in arXiv in a few days. And it seems so, yes. If I have a slow roll phase, ultra slow roll, and slow roll again, so this is the typical case. If they exit during the ultra slow roll, it just decoheres and nothing interesting happens. But if they exit during ultra slow roll and it hasn't decohered fully, for some parameter ranges, it can have this purity freezing. For some parameter ranges, it can even bounce back a little bit to have this recoherence. So it's for realistic models where you have slow roll, but with some little bit of, I think this was, we assumed like 5 or 4 e-folds of ultra slow roll, that can lead to some very interesting quantum diffusion processes, such that a quantum degree of freedom, which was decohering to classical, then freezes at some point and doesn't become classical anymore. So, and finally, this raises the question, does decoupling of UV modes still work? This was a question we asked here, and we haven't answered yet. So we know that loop corrections are under control in EFT of inflation, but what about the open EFT of inflation? Does this kind of non-unitary effects, non-local effects, means that the open EFT is also under perturbative control? This is something that's yet to be worked out, and we are thinking of how to deal with that. Okay, what's a big picture? This, I promise, is my last slide, is that we have some observable degrees of freedom in the universe, which is necessarily a part of a much larger system with an environment. And modes of interest are always coupled to unobservable stuff. An example of this is that our universe can be this, and it's coupled to some very long wavelength modes. That's the example I said in the beginning. Also, we know to have UV completion of inflation, even if you have one low energy degree of freedom, at high energies, you would have like an additional field theory or additional field degree of freedom. And what this means is that Wilsonian EFT is not directly applicable to cosmology. As I said, the integrated sub-horizon modes are not excluded by any conservation law, are not excluded by energy conservation. So what we need is some non-unitary evolution. We have a full density matrix. We trace out over the environment degree of freedom. But now the system degrees of freedom can exchange both energy and lose information to the environment and so on. So that we need to incorporate dissipation and decoherent. And both of these affects observations. As I said, it affects things like purity, affects power spectrum. And of course, if I go to higher orders, it would affect like, non-Gaussian statistics as well. So we need to write down things in terms of a master equation for just the system degrees of freedom alone. And this is bread and butter for quantum optics people, but we need to do this not for a quantum mechanical system, but for field theory, for relativistic field theory in cosmology. And people have been thinking about this, for instance, in warm inflation. One takes these dissipative effects very seriously and thinks that this is a thermal environment, whereas for cold inflation, typically people ignore such dissipative effects. And life, like most things, is somewhere in between. So we need to capture them, but not in these too easy limits. So out of equilibrium environments typically lead to non-Markovian master equations, which capture this non-unitary, non-local dissipative effects and their observational signatures. That's what we want to do. We want to go beyond perturbation theory. We have to go beyond perturbation theory for useful conceptual consequences. Master equations let us a way to do that. But open EFTs, everything I've told you about is for inflation or de Sitter space. But that's just because I chose to present on this. And this is the most widely accepted paradigm for the early universe. But this is not exclusive to inflation. In fact, we applied similar techniques to ekpyrosis, and there it leads to an upper bound on the energy scale of the bounds with Robert and one of his PhD students. And open EFTs are very useful tools, of course, going much beyond cosmology, and they're important for quantum information theory. We're applying them for de Sitter holography with Lucas Hackle at Melbourne and Xiankong at Edinburgh and Motsem also at Edinburgh, and for other things like gravitational entropy and so on. And we have applied them to different subfields, and this is a useful tool to know. Once you know this, you can apply this to black holes, to other things, and of course to cosmology. Okay, I stop here. Thank you for your attention.
Thank you very much, Sudo. Any questions from the audience?
Can you clarify, when you say Wilsonian EFT does not apply, uh, is there still a notion of relevant, marginal, and irrelevant operators? And is it somehow changed? What do you mean exactly here?
Right. So there are two different things that I want to get across here. One is that sometimes we want to observe, sometimes we want to talk about things that are explicitly not Wilsonian, not unitary. So for instance, decoherence. Decoherence means that the density matrix cannot remain pure, and that means that the state is not pure anymore. So I mean, if we have to talk about that, we have to talk about an environment and so on. So I mean, standard Wilsonian EFT, by standard Wilsonian EFT, I just mean that, you know, computing correlation functions and so on. That's not going to be sufficient there. So of course, what we then have to do is we can still do this in the path integral formulation. Everything I told you is like sort of this Hamiltonian formulation. In the path integral formulation, all of this is captured by the Feynman-Vernon path integral. And there you can do everything that we did in the Wilsonian picture, but just generalizing a little bit. I'm not so familiar with that, but one can use a similar path integral approach. But then we can ask me the question that you asked, like, can I not then write down an EFT for inflation anymore? No, of course we can. And I'm saying that we can have some hierarchies in terms of the energy scale that we are interested in divided by some heavy mass scale that will tell us what are relevant and irrelevant operators at those scales. But what I'm saying is that, and this is a very recent paper by Enrico Payer and Tomacola, where they are now saying, instead of having the usual EFT of inflation, can we write down an open EFT of inflation? So that also includes non-unitary effects in that single degree of freedom, or this Goldstone boson that one tracks for this EFT of inflation. So that would include some effects. So I'm now writing down a Lagrangian which would now explicitly have non-Hermitian terms, because those would be the non-unitary effects that one has to consider. So there are hierarchies to be exploited, but if I just do the standard EFT of inflation, we typically ignore this kind of non-unitary effects, and that is what we want to also now capture.
Is there a systematic prescription for writing those down?
Right. Yeah, that's in this paper. So the systematic procedure, if you ignore non-local interactions, but you have non-unitary interactions. So then the systematic procedure has been very recently laid out by Enrico Payer and Tomacola in a paper called Open EFT of Inflation, I think. But I'm more interested in sort of also non-local corrections. And there we don't know how to do this systematically, but we do know how to do this for toy models, and then make the model less and less toy. So make it more realistic by adding. So we essentially are saying that let's look at the leading order term from the EFT of inflation, and then saying, okay, now let's look at the next two leading order term from EFT of inflation. So, and then for this kind of systems, what kind of memory kernels do we get? What kind of non-unitary effects do you get? And you go, term by term, order by order, higher and higher. But you don't keep all the terms, because then the system becomes too complicated and you can't do anything.
Your non-locality is because of cosmology or because of interactions with other fields?
It's a bit of both. So we need cosmological backgrounds for sure to have this non-locality. That's true. Yeah. But it also depends on the kind of interactions you choose. And the kind of interactions we choose are the ones which are allowed by gravity. So they have to be sort of derivative expansions, or if we don't have derivative interactions, then there must be something that captures between like a conformally coupled scalar and minimally coupled scalar and so on. So it's a bit of both, but in general, the conclusion, I don't have a proof for this, but the conclusion that we are reaching more and more is that for gravitational systems or cosmological systems, it seems the almost any generic interaction would lead to non-local effects. Now, there can be, again, hierarchies in which you can approximate those non-local effects by local effects plus corrections. That can still be true. Yeah. But the question is, we want to find what are the regimes in which those can be approximated by local effects, and where they cannot be approximated by local effects.
And whether there's a systematic way to do it, right? I mean, because that's the spirit of EFT, I would think.
That's absolutely right. Whether there's a systematic way to do it. And as with an EFT, so it might not just be, so what generically we are finding, I can say, is that to write on EFT, all you need is a hierarchy of energy scales. Typically, when we write on EFTs in high energy physics, we say, okay, I'm interested in this energy scale H, let's say, during inflation. So I can have a very well-defined expansion in H over M, where m is some UV scale.
Right.
Or h over m squared. But now we probably would need another scale, which would be the time scale of these interactions, and you can expand in this time scale as well. And that would give you go from a non-local to a local. And that's going to be interesting in like on what time scales do the systems decohere, for instance, or on what time scales, yeah, so things like that. So there might be like double systematic way. I mean a double sort of formal power series that we have to do.
I see. You mentioned quantum optics a few times. Do people in quantum optics, do they not already have similar kind of field theory techniques? Or
Yes, they do have some. I mean, I think it's mostly quantum mechanics, but of course there are some field theory techniques that quantum optics people have obviously devised, but they're not necessarily relativistic systems. That's the main difference. So in quantum optics, you don't really often need relativistic ones, and that's one generalization that we need. But the bigger generalization, of course, is like curved spacetime. So that's certainly not something that that people have worked on. So I mean,
do they have non-local terms also?
Yes. In quantum optics, the non-local terms are everywhere. So that's not a difficult. That's the part that they understand rather well. So I mean, we have to go to Breuer and Petrichin, like one of his books, to see what does non-Markovian mean, and this kind of weird things like the entropy can have like decrease in entropy growth. That's very weird. The growth in entropy can become negative. But again, quantum optics people would say that no, that we know those kind of non-Markovian systems where there can be transient negative entropy growth. That's not difficult to understand. But those are not for field theoretic or at least relativistic field theoretic systems that they work with. They mostly work with qubits and quantum mechanics systems. But yeah, for us, those interactions are very much dictated by the curved space backgrounds. For instance, in this particular model where you find this negative entropy growth, so if you're following the green curve, this is 0, and this goes below 0 at some point. So this is like this transiently negative, as you see here. But then the point is that this is happening because the interaction is such, the interaction is time dependent. So as the universe expands, the interaction has some term like, let's say, lambda over a or some power of a. So as a becomes large, essentially the interaction quenches off at some time. It just stops. That's because of the curvature of spacetime. And because of that quenching off, it so happens that it picks out a particular growing mode of one of the system degrees of freedom and so on, such that you get this kind of a behavior or this recoherence. In quantum optics systems, you would have to quench it off by hand. You would have to say, like, I have an interaction where I just stop it, I quench off the interaction by hand. In cosmology, that's the beauty of it. It's really coming from the interaction due to gravity or the curved background.
Thank you.
Any other questions? Maybe I can ask one question. So Sudo, you didn't mention anything about the prediction on tensor to scalar ratio, probably because it's still a toy model. So do you have any idea how these non-Markovian terms may affect the predictions of?
I think it won't is the short answer, because so the tensor to scalar ratio, when we talk about that, we always mean at like the tree level, right? Like the tree level tensor power spectrum, you have a tree level scalar power spectrum. And the point is, all of these effects are quantum effects that only play some role when you do like one loop level and so on. So even if there is some correction coming from non-Markovian effects, from non-local effects, or even just non-unitary effects, those are all like at one loop level, which we haven't observed R yet. So of course we have very little hope to observe something like that. So I think our best, to be fair, like our best chance for observing something that is non-unitary would come from going beyond perturbation theory. So again, going to these tails of these PDF distributions, and in those tails, so essentially the idea there is that, well, as many of you know, but just to repeat this, sorry, let me find that. Yeah, is that, for instance, to have a primordial black hole, I need some fluctuation that's very large, but very large fluctuations are precisely the ones that are not captured by perturbation theory. So I need to know the tail of this probability distribution function to know when can I have some very large fluctuation in the early universe over some threshold, so that it produces a primordial black hole. But to do that, we can never do this using perturbation theory, because this is information about the tail of the distribution. So we have to find some other way to capture this tail. So one obvious way to capture this is like what is known as this delta N formulation. I'm not familiar with it, but that's what people typically use. But what we are saying here is that using this master equation formulation, we are also able to gain knowledge about this non-perturbative regimes. And that's what we are going to use to see for these kind of models, is it more likely or less likely to produce primordial black holes and so on if I have these kind of corrections. And that's what we want to probably focus on for actual direct observational evidence.
So I guess the prediction for non-Gaussianity is also very tiny, right?
Exactly. So
Okay.
the non-Gaussianity prediction is coming from the peak. So, and that's where Gaussian approximation is good. I mean, that's almost, that's done by hand almost, because I want the peak to match with the Gaussian, because that's what we observe. But then very small FNL approximations also can lead to big differences in the tail.
I see. Thank you. Any other questions? Okay, if no, then probably we can end the official session of the talk. Let me stop recording.